Right. Thank you very much. So it is the universally applied rule of thumb that the buffer of a router needs to be 2t times c, where 2t is the two-way propagation delay of a flow through the router, and c is the capacity of the bottleneck link. Often we don't know exactly what the round-trip time of a flow through a router is. So what people will do is they'll simply assume it's 250 milliseconds. This rule is mandated in many RFPs for backbone and edge routers. It appears in at least one RFC from the IETF. It's usually the reference where this rule comes from is usually a paper by Willem-Isar and Song called High Performance TCP and ANSNet. High performance at that time meant about 40 megabits per second and up to 4 flows. So times have changed a little since then. This rule of thumb also has major consequences for router design. And let me just give a very simple example. If today you're a router manufacturer and you want to build a 10 megabit line card, the rule of thumb tells you that you need about 300 megabytes worth of buffering. And what's worse, to this memory, you have to read and write, from and to this memory, you have to read and write a packet every 32 nanoseconds. Now, the amount of memory alone is not a problem. 300 megabytes, you can go to the local electronics store and buy that for about approximately $100. The problem is the normal DRAM that you can buy there is much too slow to be accessed at these speeds. You could instead try to use SRAM. With SRAM, you need about 80 devices, which will pretty much cover most of the space on your line card. And it'll also cost you about $2,000, and worst of all, it'll generate about 1 kilowatt worth of heat. 1 kilowatt per line card is probably more than your local data center can dissipate. So you can sort of neither of the two approaches works. And this is at 10 gigabits per second, so if you go to 40 gigabits per second, the problem becomes much, much harder. People have proposed a variety of solutions, RLT RAM, FC RAM, funneling architectures with extremely wide buses. But I think it's safe to say that for today's router vendors, building the memory architectures for these high-end line cards remains a major challenge. So in this talk, I want to convince you that the rule of thumb for sizing router buffers that is universally applied is wrong. And that is wrong by about a factor of 100. I'll first tell you where originally the rule of thumb came from, and then why for a router in the core of the internet today it no longer holds. So the reason for the rule of thumb is the congestion control mechanism of TCP. So I'll briefly sort of recap TCP, which many of you might know by heart, but for those who don't, how it works, and then sort of explain and derive the rule of thumb. TCP controls its sending rate by a congestion window W. And it has a very simple rule that says, at any given time, I may send W packets, but then I have to wait for acknowledgements before I can send any additional packets. At any given time, I may only have W packets outstanding. So if W is 3, I can send 3 packets, then I wait until acknowledgements come in. It also has a rule for updating the window size. And in congestion avoidance mode, which is the mode of long-lived TCP flows, this rule for updating W is that whenever I receive an acknowledgement that a packet was successfully transmitted to the destination, I may increase my window size by 1 over W. So if my window size is 3, I increase my window size by 1/3. If a packet is lost, I halve my window size. So if my previous window size is 10, I go down to window size 5. The result of that is the TCP sawtooth shown at the bottom here, which I think everyone is familiar with. Now let's have a look how this works in practice. So what we have here is a TCP flow from a sender to the left to a receiver on the right through a router. In this case, this router does not have any buffering. The link to the right of the router is our bottleneck link. And one of the goals we have for a router is to fully utilize this bottleneck link. So that's why I'm showing the utilization there, and keep an eye on that utilization. Currently our window size is 1. We just successfully transmitted 1 packet. We increase our window size by 1 over 1, so by 1, and now have a window size of 2. So we're sending out 2 packets. And here at the bottom you can see the plot of the current window size. Let me speed this up a little bit here. We now have 2 packets outstanding. Both are successfully transmitted, so the window size is increased to 3. If you look at the utilization is less than 100%. And it's immediately clear why this is the case. Currently, we just don't have enough packets in flight here to fully utilize this link all of the time. So this is an important observation, that the window size of a TCP sender must have a certain minimum value in order to fully saturate a link. I'm going to speed this up now, and let's see what happens when we have actually enough, a large enough window size to fully utilize the link. So window size is 7, window size 8. So with window size 8, we now have the link is fully utilized all of the time. It still shows utilization 95%, but this is just because it's always trailing a little bit. Now, the problem is that what will happen the next time my sender increases its window size by 1? When it increases its window size by 1, it'll send this one extra packet. This packet can no longer fit anywhere on the link, because basically all of the link is now occupied with packets. It also can't fit in the router buffer, because there is no router buffer. So here comes the extra packet. It gets dropped, as expected. This drop information, in the form of a missing sequence number, is now traveling to the recipient and then back to the sender. And we know what the sender will do when it receives the drop information. It will halve its window size. And when it halves its window size from 10 to 5, it'll now have more packets outstanding than it may. So it'll stop sending for a short while and then start resume sending again, but only with 5 packets outstanding. So here's the drop. Window size gets reduced to 5. Now has 10 packets outstanding, but may only have 5 outstanding, so it'll stop sending for a while. And after a short while, it should start sending again. Here we go. But now it's sending with window size 5, which again is insufficient to fully utilize the bottleneck link. And this will basically repeat itself again and again and again. We get a sawtooth. To summarize, if we have an unbuffered link, our window size will be below the threshold that's necessary in order to maintain full utilization of the bottleneck link most of the time. Whenever it touches that point where actually the link is fully utilized, it'll scale down again, and the link will not be utilized. You can actually run the math here, and it turns out that you can still get 75% link utilization without any buffering. But you cannot move, with a single TCP flow, 75% of utilization is the maximum you can get. Now let's look what happens if I have a router that has a sufficient amount of buffering. So we have the same experiment as before, but this time we have a buffer in the router, and as you can see, the queue fills with packets, and then the packets get sent out one by one. We start with a window size of 5, and as we've seen before, 5 is not sufficient to fully utilize the bottleneck link. So let's speed this up and see what happens when our window size is large enough to fully utilize the link. Have utilization 70%, 80%, 90%. So at this point, the link is fully utilized all of the time. What happens when the window size is when this extra packet is in? Here's one of these extra packets. This extra packet could not be put anywhere on the link, so it gets stored in the router, in the router buffer. So the role of the router buffer here really is to absorb these occasional extra packets, which no longer fit on the link, and prevent the window from scaling down because of a packet drop prematurely. So here we see here's another extra packet, and again, the queue length in the router increases by 1 because of the extra packet. This will continue to be that way until the buffer queue, the router queue is full. So we have about 2 spaces remaining, 1 space remaining, and now the buffer queue is full. So the next time an extra packet is sent by the sender, we'll see a drop, and the sender will halve its window size. So it's 16.8, 16.9. Here's the extra packet. Extra packet hits the router, gets dropped. The drop information, again, as a missing sequence number, travels through the queue to the recipient and back to the sender. And what the sender will do is, the sender will, again, halve its window size, stop sending for a short period of time, because now it has more packets outstanding than it may, and then resume sending, but with half the window size that it had before. So here it stopped sending, but during the time that it stopped sending, the link is still serviced by the packet from the router queue. And basically, just when the first packet from the sender arrives at the router again, the queue is empty, so we have 100% utilization all of the time. Also, our minimal window size, so the window size after the drop, was about 8.5, which is sufficient to fully utilize the link. So we have 100% link utilization all of the time. So to summarize the case of a buffered link, on a fully buffered link, the window size is always above the threshold that is necessary to fully fill the link with packets at any given time. So we have 100% link utilization all the time. The reason why the window size is high enough is that when the window grows above the threshold that basically has the link full with packets, the extra packets get buffered by the router buffer. So the role of the router buffer here is, as you can see in the upper graph, to basically absorb these fluctuations in the window size of TCP. So how much buffering do we need? We need enough to buffer in order to fit the sawtooth of TCP. If TCP wouldn't have a sawtooth, we wouldn't need buffering in router, or we need at least much, much less buffering in router. And this is the origin of the rule of thumb. If you plug in the numbers, and if you're interested in the math, there's a SIGCOMM publication from this year that has the equations. It actually turns out that you need exactly 2t times c, that the height of the sawtooth is exactly 2t times c. So to summarize, the rule of thumb makes sense for one flow. Now, the routers that you here in the room are all operating have more than one flow. They typically have in the thousands or 10,000s of flows. So the question is, if we go up by 4 orders of magnitude, does the rule of thumb still hold? The answer is, if the flows are perfectly synchronized, then the rule of thumb still holds. If the flows are desynchronized, then the rule of thumb doesn't hold. This brings me to the second part, which is what is the correct amount of buffering that's needed for a router, for a congested router. And the result will be that it's 2t times c, so our old rule of thumb, divided by the square root of the number of flows. So if we have more than one flow going through a router, the role of the router buffer is to absorb the fluctuation in the total number of outstanding packets. So instead of absorbing one single sawtooth, it now has to basically absorb the sum of all these sawteeth. If the flows are perfectly synchronized, we basically have small sawteeth that add up to one large sawtooth, so we have exactly the same dynamics of the number of outstanding packets that we have for a single flow. We also have the same buffer occupancy that we have for a single flow, so the rule of thumb still holds. If flows are not synchronized, it is more complicated. Here we have at the bottom shown 2 flows that are not synchronized, so basically we now have a slightly randomized sawtooth. And the sum of these randomized sawteeth, what we expect to see is some kind of statistical multiplexing. We can make a very simple quantitative argument here, and I'll spare you the math again if you're interested, it's in the paper. But if we assume that each of the window sizes, the window size of each flow is an independent random variable, then the central limit theorem tells us if we take the sum of independent random variables, it should converge towards a Gaussian distribution. Does anyone still remember that from calculus? Yeah. So that's something which we can very easily verify. So we take a network simulation with NS2. We plot the probability distribution of the sum of the window sizes. And we did that. And what you actually get is something that looks pretty much like a Gaussian. So in this case, this was for, I believe, 100 megabit link with thousands of flows. Well, or about 1,000 of flows. So how much buffering do we need in this case? We said the role of the buffer is to absorb these fluctuations in the total number of outstanding packets. The probability distribution of these outstanding number of packets is this Gaussian. So we basically want to pick a buffer that will bracket our Gaussian. So that'll basically be big enough to fit the Gaussian most of the time. So the probability of so many packets being outstanding that we're above our buffer and we get drops is small, and the probability of so few packets outstanding that we're below the buffer and effectively don't have 100% utilization is also small. And the central limit theorem also tells us that the more variables we have, the more statistical multiplexing, and the narrower the Gaussian gets. The width of the Gaussian decreases with 1 over square root of n, as you can look up in most math books. So the buffer size, which is necessary to bracket the width of this Gaussian, also decreases with 1 over the square root of n. We know the buffer for a single flow is 2t times c. We've seen before that for a single flow, the rule of thumb still holds. So the amount of buffering required for n flows should be 2t times c divided by the square root of n. So what I'm saying here is that actually the more flows you have, the less buffer you need. I think this is about the only thing in networking that gets better the more clients you're serving. And again, this is something which we can very easily verify using an NS2 simulation. We have on the x-axis here the number of flows, and on the y-axis the minimum buffer that we found basically iteratively. So we just reran the experiment until we found a buffer size that would guarantee us 95% good put. And we can see that the red dots, which is our simulation, fit very well our model of 2t times c over square root of n, which is the green line. So to summarize, for a congested router, Flows in the core of the network are desynchronized. There's plenty of experimental evidence for that, and also if you run a network simulation, once you get enough flows, they desynchronize. And for desynchronized long-lived flows, you need only buffers of 2t times c over square root of n. Now we said before, n is something like 10,000. So what I'm telling you here is that if you take your current router today and switch off 99% of the buffering, it'll run better. You don't need to change anything in the protocols, any other external network parameters, but basically this will still be sufficient in order to absorb fluctuations in the total number of outstanding packets. It'll also reduce the overall latency of flows through the router in case of congestion. And then we have later some experiments to back up that claim. Now, so far, we were assuming that we have a congested router with long-lived flows. You might wonder, what happens if we have flows in slow start? The majority of flows in the network actually are typically short-lived flows, for example, web traffic, that only sends a few packets before the flow terminates. These flows never get out of slow start, never get into this congestion avoidance mode. And in that case, buffer requirements differ. And the answer is yes, you actually need even less buffering. Unfortunately, if you mix long-lived flows and short-lived flows, as you have it in a real network, the effect from the long-lived flows dominates. And even if only 10%, in a typical network today, probably something like 80–90% of your packets are from long-lived flows in congestion avoidance mode. Even if there was only 10%, still the long-lived flows will dominate. So basically, a very small percentage of long-lived flows is sufficient in order to have the long-lived flow effect dominate your buffer requirements. But if you have a router where you know this router is never congested, you never have any long-lived flows, then you can actually get away with even smaller buffers. So in slow start, TCP has a different way of updating its congestion window. It'll start out with a congestion window of 2, and then basically double its congestion window for each window worth of data that was successfully transmitted. So TCP will first send 2 packets, then 4 packets, 8 packets, 16 packets, 32 packets, the distance between these bursts being 1 RTT. I'll spare you the mathematical model that sort of to model these short flows. It's basically a queuing theoretical model. We can, with this model, calculate things like loss rate, average queue length, or the flow completion time, so the time from starting a flow to ending a flow. The complete model is in the paper. Here's just a brief overview of what the result means. What we've plotted here is the average queue length you're going to see in your router if you only have short flows. At the bottom, we have the flow length in packets. So assume we have only flows of length 20 packets, which would be probably be like a small web page. Then the average queue length you would see is only 10 packets. This depends on what load you have in your router. This is assuming a load of 80%, which is already fairly high. The important thing to take away here is not so much what the exact quantitative relationship is, but 15 or 20 or 30 packets worth of buffering is all an extremely small buffer. I mean, today, routers typically have thousands or 10,000s of packets worth of buffering for high-end routers. Other results from the short flow model. Most importantly, the buffer requirements only depend on the length of the bursts and the load. They do not depend on the line speed and the RTT. To give an example, if you have bursts of up to size 16 and a load of 80%, for 1% loss probability, you need about 115 packets worth of buffering. If you double that buffer, you get another factor of 100 smaller loss probability. So basically an additive increase here in the amount of buffering will give you an exponential decrease in the amount of in your loss probability. Bursts of size 16 might seem small at a first glance, but for example, Windows XP usually doesn't scale its window size above 12 packets. So this is actually a fairly realistic number. But the most important takeaway is that all this the amount of buffering for these short flows that you need does not scale with the line speed. So if you build a 1 megabit router or 40 gigabit router, as long as it serves the same type of traffic and just more of it, the amount of buffering you need does not change. And what this means is that the amount of buffering you need for the long flows, which increases with the bandwidth, usually is the dominant of the two effects. So I now want to show you what happens if you actually try this out with simulation and real physical networks. So this is a comparison of 3 things. Simulating our model with, well, first of all, our quantitative model, so basically just using the formula that I just presented. Simulation of a network using NS2. and experiment on a real physical Cisco GSR router with OC3 line cards.
What engine line card?
That's a very old one. It's an engine 0. Okay. So we repeated this experiment first for 100 flows and for 400 flows, and then we picked router buffer sizes of 2t times c over square root of n, half of that, 2 times that, and 3 times that, just to get an idea for sort of the elasticity. How exactly does it depend on the amount of buffering that you have? And you can see in the numbers to the right that there's fairly good agreement between model simulation and experiments about two things. A, that with 2t times c over square root of n size buffers, you can achieve very close to 100% utilization. If you have 400 flows, actually 100% utilization. The 99.9, the experiment is probably a statistical error. It also shows that the model roughly predicts correctly at which point utilization will drop from 100% to something below 100%. So this formula of 2t times c over square root of n in a laboratory experiment with traffic that we generated ourselves does actually work. We also tested our short flow model. So this shows the probability distribution that the queue exceeds a certain length on a router. So we have the probability on the y-axis in logarithmic scale, and the queue length on the x-axis. And we can see that the model, which is the blue line, fits very well with two sets of experimental data, which is the red and the green line. That is, if you shift the data by 42 packets. And at first this puzzled us a lot. We didn't see any good reason why we would always underestimate the queue length by 42 packets. But then we started running numbers, and 42 packets or 43 packets corresponds to 65 kilobytes of data. And so we were thinking maybe there's somewhere is a hidden memory here of 65 kilobytes that is not documented in the router documentation that we can't measure. If there's sort of some additional buffering of that size, it would explain why we always measure a queue length that's off. And so we actually contacted the manufacturer and found the person who built the line card, and they told us, yes, it's actually true. In the interface management chip, there's a 64 kilobyte buffer, and with this offset, the theory and the experiment match extremely well. So we decided to go one step further and try this out with live traffic with real users. So far, the experiment on the GSR that we did was basically an idealized setup in a laboratory. So we only had long-lived flows. We had very controlled traffic. We only had TCP. But we had real PCs with real TCP stacks. In this experiment, we took a live production network while it was running, throttled the bandwidth until we got congestion, and then reduced the buffer size to see when utilization would drop below 100%. And big thanks to Leo Roberts, Sunny Young, and Wayne Sung from Stanford for allowing us to do that. And it turns out that with small multiples of 2t times c over square root of n, which is shown here in the second column, we can get, in the experiment, so the rightmost column, utilizations that are very close to 100%. So even for traffic that's a mix of long-lived flows, short-lived flows, UDP traffic, probably occasional denial of service attack or something like that, even under sort of this much more diverse traffic mix, this rule still holds fairly well. We also tried this on the Internet 2 research network. So we took the link from Indianapolis to Kansas. This is a 10 gigabit per second link served by two Juniper T640s on each end. The default buffer of the Juniper is about 1 second. And on this link, we have occasional test flows of 1 gigabit per second. For a TCP flow of 1 gigabit per second with normal TCP, we need very, very small loss probabilities, somewhere in the order of 10 to the minus 8. So this is extremely stringent loss criteria we have to fulfill here. So the first experiment was to reduce the buffer size to 10 milliseconds, or 1% of the default. Nothing happened. 5 milliseconds, still nothing happened. The next step is 2 milliseconds, so the experiment is ongoing. But so far, there was basically nothing that there was to observe. The test flows would still have the full utilization. We would not see any packet drops on the link, even with these small buffers. Thanks to Stanislav Shalinov and Guy Alms who helped make that happen. So to summarize, the old rule of thumb for how much buffer a router needs is 1 delay bandwidth product. And There's still certain cases in which this rule holds. First of all, if you have a single flow that should be able to saturate your router at full speed, then you still need a buffer of 2t times c. If for a single flow you can live with 75% of the utilization, then actually you can use much smaller buffers. So if you want to set, for example, a new speed record, large buffers might still be necessary. However, if you're serving many flows, even if you have congestion, then you only need buffers of 2t times c over square root of n. And we believe this is applicable for the core and the edge of the network today. If you have one or many flows and you have no congestion, and you know there never will be congestion on this router, then you can actually get away with even smaller buffers, something in the order of 100 or maybe 200 packets. It's fairly independent of line speed. It just depends on how close you want to get your load to a 1. I mean, again, this is only for uncongested routers, so if your load goes above 1, you'd be back in the upper case. But this only works if you know your router will never be congested, and which probably for a real network is not a particularly sensible architectural design guideline. Because if a link goes down or something like that, you might get congestion. So this change has a fairly large impact on router design. If you have a 10 gigabit line card serving 200,000 modem flows, which sort of is the last generation of line cards, then the rule of thumb tells you need 2.5 gigabits worth of buffer memory, which would require external slow DRAM. With a new rule of thumb, this buffer now becomes 6 megabits. 6 megabits you can easily put not only in SRAM, but put in on-chip SRAM. So you don't need any external RAM devices for buffering anymore at all. For a 40 gigabit line card with 40,000 broadband flows, we still need the reductions from 10 gigabits to 50 megabits of buffer memory. 50 megabits today is just slightly too large to put it on chip, but the people who understand how to build these things tell me that in the next generation of chip design, it should be possible to fit something that order of magnitude on the chips directly. I think currently you can do 32 megabits on SRAM chip, but the next generation you will be able to do 64. So that buffer also could go back on the router chip. And with that, thank you. If anyone wants to know, wants to have more information, we have a lot more experimental data and all the math. There's a paper on our homepage, and I open it up for questions.
I have a question over here. Have you noticed in your experiments any reduction in latency along with reducing the length of the queue or the buffer, and is that significant enough to be another good argument for doing this?
So, yes, absolutely. I didn't touch on that, but if you have buffers of 1 delay bandwidth product, right, your maximum queuing delay is sort of the amount of buffering you have divided by your line speed. So if it's 2t times c divided by c, so your maximum queuing delay is 2t, which means in case of congestion, the latency through the router will just be twice what it is without congestion. So effectively, the existing rule of thumb sort of doubles latency in case of congestion. With the new rule of thumb, you get to the increase is a % or something like that over the latency without congestion. So we have a much smaller increase. Even more interestingly, I mean, one of the questions that came up is if we have smaller buffers, we might get a little bit more loss. So for example, does this hurt short flows in mixes of flows? If we have long flows and short flows, do short flows suffer from smaller buffers? And it turns out no, they actually, because the much shorter RTT through the router outweighs any longer
additional
completion
loss
time due to losses or timeouts by an order of magnitude. So if you have smaller buffers, basically in case of congestion, your short flows will take half the time or close to half the time to complete.
Thank you. It's very interesting.
Hi, Scott Marcus. A very interesting piece of work. I was curious, since in the comparisons between the theoretical, simulated, and actual results, all the numbers are pretty close to unity. I assume your sample sizes were probably pretty large. I was wondering about the confidence intervals.
So let me see, which of the slides were you referring to? It's different for different ones. So for the Stanford experiments, the biggest problem was estimating the number of concurrent flows. So basically our n. And n is only in a square root, so we're not particularly sensitive to misestimating that, although there we're not particularly precise. We could be off by as much as a factor of 1.5 or 2.
Okay, thank you.
in the other experiment here, we're much more precise because we could control the setup. So here I would say we're probably within 0.1% or 2%.
Okay, so your confidence intervals on each of the individual percentages you're saying is probably within 1.1 or 0.2%, you think?
Yes, that's correct.
Okay, thank you.
Did you give any consideration to how routers prioritizing queues, for example, weighted fair queuing or class of service, impacts this? Does this model apply to that, or is that a totally different experiment to factor that in?
We thought about it a little bit. I mean, for the experiments in here, we just assumed that we have one output queue, right, which is slight oversimplification over what you have in a real network. If you have multiple virtual output queues that are completely separate, then basically you would have to, each output queue would have, by itself, would need to have this amount of buffering. You can, well, okay, this is a slight overestimate. You can get some amount of statistical multiplexing between them, but it would be less than if you just had one queue.
John Lee. I had a question about what packet sizes you were using, and did you have variable packet sizes in your flows?
So in our simulations, as well as the GSR experiments, we just had long flows sending at maximum rate, sending infinite amount of data. So they would always have maximum length TCP packets one way and X going back.
So that was 1,500, or was that jumbo packets?
1,500.
Okay.
For the Stanford experiment, we had a wide range that, what is typical for a production network today. So we had some short flows, we had some streaming applications with like 300 to 700 byte packet lengths. We still had probably around a third or half maximum 1,500 byte packets.
Okay, thank you.
Wanted to ask you if the cost factor by increasing the buffer size, decreasing the buffer size by a factor of 100, how much does it like what's the net result in terms of the overall reduction in cost of the router?
So I guess we have a lot of people in the room here who can probably answer that better than I could. So what I've heard from router manufacturers is, first of all, the RAM chips themselves. I mean, typically today for router you have to use DRAM at the end of the day because that's the only RAM chips that'll give you enough amount of buffering. The cost of the DRAM is negligible. It's in the order of hundreds of dollars. However, the architecture that you need in order to access this DRAM, so typically these sort of staged part SRAM, part DRAM, very wide bus architectures, they tend to make the line cards both more expensive as well as much more power hungry. So estimates I've heard, and this is, I can sort of just pass this on, were that between 30 and 40% of the cost and complexity of a line card today is the buffering architecture. So if you could all move it back on chip, you might be able to reduce it by roughly that amount.
Thank you. One more quick question. Have you considered the effect of correlations, like if you have on-off sources with long on periods? It's well known that the superposition of such sources is highly correlated going into the buffer and the way they interact in the buffer. Have you considered that effect of that type of correlation? So in our models, no. The trace data that I've seen for sort of core links in the network typically show data that is fairly well behaved in terms of its overall behavior. So there's no strong synchronization at any time scale, and not at any time scale relevant for sort of the analysis that we do between flows. So I guess my answer would be, in the traces of the network that I've seen, I didn't see that effect, and so we didn't look at it in more detail. If you have a network where this plays a major role, that you'd have to look at that separately. Thank you.
Two quick questions. First is, did you model or test any topologies involving multiple serialized routers, some with regular size buffers and others with the new model buffering, and especially at different speeds?
Okay, so we looked at topologies where we have, for example, access links that are slower, or somewhere in the path we have routers that are links that are slower than our bottleneck link, right? Which is typically the case in the core of the network. If you have a 10 gigabit link in the core of the network, hardly anyone has a 10 gigabit access link to the core. And in that case, so generally slow access lengths smooth out traffic. I mean, because basically if a quick burst will space out as individual packets and arrive at the core router as individual packets, and this is beneficial. We did not look at scenarios where you have multiple points of congestion in the network. That's an open question.
I guess my question was really, even if there was only one congestion point, would it matter where the buffering was actually reduced?
So the answer is we looked at some scenarios there. We think that sort of covers most topologies with a single point of congestion. And what I've presented here is a worst case estimate. So if you have, there are other topologies where I might need less buffering because basically traffic is smoothed out in the axis. Does that answer your question?
Kind of. I'll follow up afterwards.
Okay.
The other question is, for the internet speed land record stuff, would that not be a case of, would it make not more sense for them to have modified versions of TCP that don't do the window and half, using a more modified?
Absolutely. I mean,
because once you've got the small buffers, then they need to work around you.
Yeah, no question. Absolutely. I mean,
quick question for you. Does your data include, admittedly I have not read your ACM paper, so perhaps it does. Does your data include any kinds of simulations or tests in which you had a combination of conformant to loss, like TCP of course, and non-conformal flows like voice over IP or TDM over IP, that kind of thing?
So we did combinations of short-lived flows and long-lived flows. And while short-lived flows, they still in theory adapt to congestion if they lose a packet. In practice, they are so much more aggressive than the long-lived flows because they have smaller window sizes and just double every time that you can almost treat them as a sort of a constant rate sender or something like that. And that doesn't change the results.
Well, I guess the one question or more concern I would have in my mind is, for example, on a network that we know is going to carry largely RTP traffic, would those non-conforming flows tend to exaggerate the capture effect if you had less and less buffer at congestion points?
So we should maybe take that offline. Sometimes yes, sometimes no.
Thank you.
Hi, if you change from square root of n to say cube root of n, did you have some sample, results for those kind of changes to buffer size?
I'm sorry, I didn't get the first part of the question.
If you change from square root of n to some other number like cube root of n.
Okay.
So
yeah.
It's 2t by c by cube root of n. Did you, could you comment on that as to how it changed the throughput?
Yeah. So the fundamental question there is what happens if you pick a buffer size that's too small or too big, right? And if you look at the shape of the Gaussian, right, it's fairly sensitive to. If you pick much too small a buffer, you're immediately going to recognize it because your losses just will become huge, right? And you're not going to go anywhere near 100% utilization anymore. If you pick a buffer size that's too large, you'll still get 100% utilization, but with a larger latency. And this transition is actually fairly sharp. So if you would take, I don't know, 2t times c over like the cubic root of n or something like that, you would get a much less than 100% utilization and significant losses. Does that answer your question?
Yeah, I was looking at some, experimental results if you have done in this. Is there in your paper or some data point which is looking at this?
So there's some in the extended version of the SIGCOMM paper that's on our homepage. There's some data on that compares sort of how varying your amount of buffering affects utilization. So if you get 99.5 versus 98 or 99.9, you might want to have a look at that, or we can follow up.
Thanks.
Okay.
One quick question. Was there any investigation of red or other similar discard mechanisms other than tail drop?
So yes. The key effect of red is that it desynchronizes flows, which my whole analysis here is if you have synchronized flows, then you still need the large buffers. If you have desynchronized flows, you don't need the large buffers. I don't claim to fully understand when flows are synchronized and when they are not. The big problem is that the NS2, which is the standard tool in the academic community to to simulate networks tends to overestimate synchronization. So if NS2 shows you synchronization, that doesn't mean you necessarily have synchronization on a real network. Red, if you have synchronization, you use red, it will definitely help you to desynchronize the flows and get to your lower buffer requirements earlier. For a very large number of flows, flows tend to be synchronized with red or drop tail or any other scheme, so it doesn't really matter what you use. I mean, if you have like more than 5,000 flows, use whatever you want to. Thank you.